All right, welcome back. Let's talk about related rates. Related rates involves the tracking of changes in one quantity while another quantity is also changing. And we're talking about more than two variables necessarily. It could be three or four variables where you have formulas from geometry, physics, finance, or what have you. In any case, what ends up happening is you're just jumbling a bunch of variables and dealing with implicit differentiation with respect to time. So let's talk about the typical equations that you might see. Here we have the area of a square. And remember, the derivative is with respect to time, not to a or x. So we do the derivative of a, which is just dA dt. And then we're going to do the derivative of x squared, which is 2x. However, that is then implicitly differentiated with respect to time, giving us a dx dt. Simply put, if you don't know what to do, take the derivative and then stick a d by dt at the end for the respective variable. Moving on to the area of a rectangle, here we have a generalization where the area involves two variables, x and y. The derivative of a, simply put, dA dt implicitly with respect to time. And then we'll have a product rule on the right-hand side. So we'll have here a template for the product rule. The derivative of the first part, which is dx dt, you hold the second, then you hold the first, and do the derivative of the second part, which is dy dt. How about the Pythagorean theorem, or in other words, the equation of a circle? Now, in general, all these terms are not necessarily variables. Some parts could be constant. And we'll see an example, for example, where the hypotenuse or one of the legs is constant. And there you see here, we do the derivative of x squared and get 2x and then dx dt. Then do the derivative of y squared, which is 2y dy dt. And then r squared, which is 2r dr dt. We can cancel out the 2's. And end up with just that lovely equation. So you will refer back to these equations during the video. You might have to pause or maybe just jot these down, but I would definitely recommend putting these in your notebooks. Area of a circle. So the area of a circle is pi r squared. Now pi is not a variable, but we'll do the implicit differentiation with respect to time for both sides. So we have dA dt on the left, and the derivative of pi r squared, well, the derivative of r squared is 2r. So we have 2 pi r, and then don't forget implicit differentiation with respect to time, dr dt. Volume of a sphere, it's a cubic function with respect to r, so let's do that here. We have dv dt on the left, and then 4/3 times 3 just gives you the 4, so that's why you see a 4 pi r squared. And don't forget implicitly that r differentiated with respect to time is dr dt. Surface area of a cylinder, here we have three variables. We have the radius, the height, and the area. And we will require some product rule here as well at the end. So you could also group this differently. You could factor this equation. In any case, I'm just going to leave it as separate terms. So we have here the derivative of 2 pi r squared, which is 4 pi r, implicitly then dr dt. And then over on the 2 pi rh, we require a product rule. So I'll keep the 2 pi with the r. So we'll have your 2 pi times 1 dr dt, or 2 pi r dr dt. Leave the h alone. Leave the 2 pi r alone. And the derivative of h is 1 dh dt, or just dh dt. How about the volume of a cylinder? Okay, another product rule here. So we'll group the pi r squared together. So the left-hand side derivative. And then the product rule here, we have 2 pi r dr dt. And hold the h, hold the pi r squared, and then finally differentiate h with respect to t, which is dh dt. How about volume of a cone? Well, if you look back at the volume of a cylinder, it's basically the same thing, except there's a factor of 1/3. So what you saw here is I basically copied the cylinder's derivative. You can refer back to the previous example. And then I'll just include the factor of 1/3. In other words, introduce a 3 to the denominator for each of the two terms presented. Okay, let's talk about some application questions. So here we have a circular puddle that is growing at a rate of 2 centimeters every second. How fast is the area growing when the radius is 5 centimeters? So area of a circle, okay, circular area, write down the area of a circle. Before I do that, though, let me just list the working variables, which are r and a. Do we know any of these things? We'll figure it out shortly. And also, I like to write down their derivatives. with respect to time. This is like my checklist. I recommend using a checklist like this when doing questions. So anything we know here? Well, we know that the radius is 5 centimeters, and we know that the rate of change, dRdt, is 2 centimeters per second. Pay attention to the units. So like if there's centimeters and millimeters or feet and yards or whatever the heck it is, make sure that you write them all consistently with the units. We want to find dAdt, and we don't actually care what the area is at that instant of the radius being 5 centimeters. So let's write down the area of the circle. We can write down the rate of change version of that equation with respect to time. Now, looking here, you can see that we have everything that we need to find dAdt. So these brackets here will be populated by the information on the left. We know the radius is 5. We know the rate of change of the radius with respect to time is 2 centimeters per second. Multiply 2, 5, and 2, and throw a pi in there, and you get 20 pi. You can write that as a decimal, but I'm going to leave the answer in exact form just to avoid using a calculator. Anyway, that is the first example. We'll escalate the difficulty with a few more examples and see how this goes. In this next example, we have a rocket being launched, and we see that the observer is standing on the ground 600 meters from the launch site. We want to see how fast the distance between the rocket and the observer is changing when the altitude of the rocket is 800 meters. Now, it's a Pythagorean theorem question. You can draw a triangle for that. But don't make variables everywhere. So when I wrote down the Pythagorean theorem earlier, I had x, y, and r. Here, if you don't need it, don't use it. So for example, there's my rocket, fancy rocket, eh? And there's the observer, stick figure person. And this number is 600. I could call that x, but why bother? It's fixed. So I just put 600 there. This will make the math a little bit easier later. H, well, I could have called it y. I called it h here. It's all good. And then the distance between the two objects, the rocket and the observer, is L. You can call that R if you like. Let's write down the variables. So in this case, we have H and its rate of change, and then the variable L and its rate of change. Just like the previous example, I've made a little checklist here, and I'm going to put all the numbers that you need here, what you have, what you want to get. You could pause the video and figure this out first. We know that the height is 800 meters at that instant. We know that it's growing, the height is growing, or it's rising at 200 meters per second. We want to find the rate of change of L with respect to time. Let's write down a static equation. See, this equation is just your basic geometry equation or formula for an area or volume, or in this case, a length relationship. I'm also going to write the rate of change of that equation on the right. It's like what we derived earlier, except that there's a 0 where the 600 squared is, because 600 squared has a derivative of 0. We could simplify on the equation for the Pythagorean theorem by plugging in the height of 800 and then getting L. Why are we getting L? Well, it wasn't obvious until I got to the rate of change equation and I noticed that there's an L right there that we needed to figure out. So getting back to business here, we can see that L equals 1,000 meters. Yes, these numbers are very friendly. Typically on a no calculator test, you'll see friendly numbers. So if this was more of like an application with a calculator question, you're just going to get dirty numbers. Perhaps you're dealing with different test versions or what have you. So we can plug in that 1,000 meters into the appropriate position in the rate of change equation. Here we go. So firstly, I'll just cross out those 2's. And now we want to find the dLdt. So we're good to go because we have the other 3 quantities. So I'm going to just solve for dLdt. You could plug the numbers in right away, but I'm going to solve for dLdt first. And then you can plug in H, L, and dHdt. There they are. Clean it up. If you notice, the meters in the fraction, the first fraction, cancel. So you do get units of meters per second. And the answer is 160 meters per second, which ultimately is all you need to do. So bottom line for this example and the previous one was just write down the static equation, find the rate of change, plug in the information based on your checklist, and hopefully things work out. In this example, we have a ladder that is resting against a wall, but it's being pulled away from the wall at some rate. So that means if you pull away at the bottom of the ladder, it's going to slide, and then the top of the ladder will fall. Perhaps a picture's in order. Here we go. So you see X here, you're going to pull X. X is going to get larger. So this ladder is going to slide against the wall, and that value of y is going to reduce. The ladder is always 10 meters, so don't put r there, don't put hypotenuse, just put 10. No variables. So our working variables are x and dx dt, and then y and dy dt. And you can plug in the information here. So we know that the base of the ladder is 4 meters from the wall. We know that it's being pulled at half a meter per second. So that's plus 0.5 because it's growing. We're going to expect a negative answer for dy dt because the ladder is falling. We don't know what that is yet because that's the final answer. We don't know what y is either, but we'll get to that because we know the Pythagorean theorem. So we have the static equation, the one that is just fixed. And then we have the dynamic one, or the rate of change version. I say static and dynamic. It's more of like a physics thing from all the training that I've done in school, but it just works for me. So there you go. Let's find out what y is, because as you can see in the rate of change equation, we have a y. So plugging in the numbers that we know, we can see that y ultimately will equal the square root of 84. Yeah, you could simplify the root, which I did, as 2 root 21. I am probably gonna rationalize the denominator in the answer, so we'll get to that point anyway. So if you don't like roots, you might have to brush up on your roots to see the ending of this question. Okay, I promise to make it as not as painful as it could be. Anyway, let's go back here to the rate of change equation and just plug all the numbers in. So in contrast to the previous example, here I'm just plugging the numbers right away. I didn't put the units down, but I'm going to be very safe to say that the answer will have consistent units because we have meters and seconds throughout, and we expect dy dt to have units of meters per second. So 4 times a half is 2. Let's move that 2 over and then divide by 2 root 21. Now here, this answer, most times you just get full marks for this, but you might get the odd like evaluator that will say, oh, rationalize the denominator. And I want to respect that process. So I'm going to multiply by root 21 over root 21. And if you clean it up and cross out those 2's, you do get this answer, which confirms our work is done here. So anyway, one more example. I think that's going to be enough for this. Probably have saturated your brain with rate of change and related rates. Okay, so here we go. One last one. Let's do a sphere. So here we have a sphere that is being inflated at some rate. It's a volumetric rate. And we want to find out what the surface area rate of change is when the volume is at some quantity. So we're juggling 2 formulas here: volume, which is the volume of a sphere, and its rate of change, which we covered earlier in the video. Might have to flip back. I don't know how long this video is, but maybe like 5 minutes, 10 minutes. And then the other equation, which is surface area, which is right there. And then its derivative, which is right here. Now, essentially, you could just plug in all the numbers everywhere that you can, and hopefully algebra is going to win the game for you here. So we know that dv dt is 72, and we know the volume is 36. So that's kind of our working area. So based on the 36 pi, we can plug that in here and solve for r. The numbers look a little bit daunting, but they actually work out really well. R is equal to 3 once you take that cube root. Now let's go to the rate of change of volume, which is 72 pi. I don't think I said the pi on the 36, but this video is done in one take, so it's all good. Anyway, let's plug in the r that we know, which is 3. You could have done this step first and realized you need the r. So you're going to go back anyway to find it, the purple area there, the purple region. Anyway, let's clean that up. 72 divided by 36 is very nice, and the pi's cancel. So we get a rate of change of 2 inches per second. I like that. Now, we need the rate of change of surface area. So this third equation, S area, we don't need it. So just don't use it. So I'm going to plug, oh, there we go. Just plug in some stuff. So we know what R is. We know that R is equal to 3. I color coded them. So hopefully, if you're not good with the colorblind stuff, I apologize. I had a classmate one time that did a video in grad school, and it was like for fluid dynamics, and it was red and green or something, and it was a presentation with fluid mechanics and flows and things like that, except they used that color scale. So the one student, my classmate, who's colorblind in those colors, was like, dude, I can't see anything on the screen. It just looks like water to me. Anyway, so I'm trying to be very attentive to that. So let me know in the comments, are the colors good here? Do we need to have some some corrections. Anyways, you can see here. Hopefully, you can even mute me at this point. Um, Probably are 48 pi. Okay, and the area has units of inches squared per second. So there you have it. If you could do these questions, you're good to go. And if you want to see more of these, I might put them in separate videos, like smaller ones or shorts.